Hi, thanks very much for the introduction. My name is Peter Rakich. I'm a professor in applied physics at Yale University, and I want to tell you about a new startup company we've started. It's a spin-out from Yale University, Resonance Microtechnologies. We're all here because quantum networking, quantum computing, quantum sensing are poised to really change the world, and we see there's some key challenges of scalability we'd like to address with new technologies we're offering. So the main problem of scalability, you can see if you work on atomic-based quantum computing or quantum networking or sensing, is that you walk into a laboratory and you see typically a table full of components like this that are painstakingly aligned. This is really not a scalable approach. We desperately need something that's more integrated. We can do co-integration of photonic circuits and electronics on chip scale technologies. This is really what we need to employ, and we can leverage many investments from AI, computing, classical computing, and networking. The problem is there are some missing components that just don't exist in these conventional integrated platforms. A key challenge here is we lack cavities, very high performance, what I'll call quantum cavities. These are devices that are used to control and capture the emission from atoms in order to make efficient networking possible. Traditionally, these are constructed by polishing, grinding, hand assembly. This approach, you see the prototype on the right. This approach certainly isn't going to work. You can't put thousands of these into a blade server. You couldn't hope to do that. What we've done at Resonance is, at my group at Yale, is develop a really transformative new fabrication technique that allows us to create ultra-high performance cavities that really have been out of reach with conventional fabrication techniques, and to do this at scale on a wafer. So we've shown that we can produce hundreds or even thousands of these on a wafer with very large-scale batch fabrication, yielding performance that a lot of folks would dream to have, could only have dreamt of before this approach. So this technology, just to tell you a little bit about it, it's the offshoot of two very successful DARPA programs. We've got a number of patents around this technology and the new fab technique and various integration techniques that we've pioneered under these DARPA programs, the strategies to both produce the cavities, assemble them, and integrate them with planar photonic circuits that are scalable in approach. So where are we now? So we've been working over the last year on a lot of industry engagement, talking to customers, understanding exactly what modules, what devices are urgently needed. And we've identified two different sets of modules, both feeding into the quantum ecosystem. Some of them are components that are needed now to feed various optical systems, and others are really about helping us control atoms inside or emitters of various types in quantum systems. We see the potential to, if we play our cards right, 5 to 7 years, capture as much as $200 million of market. We see a lot of potential in particular in quantum networking and a lot of the hardware that feeds the quantum ecosystem, from stable laser systems to quantum sensing systems. So we've been lending out these demo parts that we've produced through over the past couple of years to a couple of vendors. We're getting a lot of interest. We have several vendors that are lined up that really would like to get their hands on these. We have a couple of pending proposals, a couple of $1 million each, with medium-sized quantum startups. And we're right now, if you were to invest in us with this award, we'd be working on hiring a production engineer and fulfilling orders and contracts, which we think we could do within the first year. So thanks to my team, and please reach out if you have any questions. My co-founder, Greg Luther, is in the audience, so thanks.
Hi, Peter. How are you? We spoke a few weeks ago, but you went really, really fast.
Yes,
really like the part of the supply chain resiliency. It's obviously something we track very closely at JP Morgan. Just go a little bit over that in terms of how does it compare with other things in market, and what is the angle on the supply chain resiliency aspect?
So there's a couple of different products that there are some products that we see great need for now, almost independent of quantum, but this device and the performance that it can bring to different laser and optical and sensing systems is pretty integral to quantum systems. So as a lot of vendors are building new types of optics and laser systems, They have their mind towards scalability. They know that the way that trapped ion systems are built right now just isn't going to work. They're using really big lasers. Everybody needs to shrink it down to make it compatible with autonomous vehicles, a lot of different things. So we see a lot of opportunity. What we're offering for our solution is a radical change in size and scale of the device that is normally used for these to achieve this high performance.
And near-term revenue opportunities.
Pardon?
And near-term revenue opportunities.
Near-term revenue opportunities. I mean, we have a number of customers we're talking to that would, they're giving us volume estimates for how many they would like. We don't have enough of these parts to loan out to vendors right now. So we're shopping the parts that we do have and giving them a short leash of 2 months to evaluate it before they send it back. But that's where we are. And I should mention that our cavity performance through these publications validated by NIST. So we've got a lot of credibility there.
I saw the size of your system looked to be about 9 millimeters there. How small can you scale that down to?
So that was one example, slightly out of context. Mm-hmm. We can make cavities that have basically much smaller volumes. So basically 100 microns by 100 microns kind of thing, or
Is
less.
That hypothetical or in production today?
Pardon?
Is that hypothetical where you can scale to, or what you could produce today?
It's been demonstrated. So we haven't. So it's a slightly longer discussion. But yes, we've proven that this is possible. We have not yet made this particular form factor to solve problems of a particular type we want to solve. But we've shown that it's possible.
Just to give me a good understanding, what's the next best alternative size for this kind of system?
So there are. Okay, next best size, but my comment would be no vendor that we're aware of can at scale produce the performance that we have. So there's certain mode volumes that we can hit that nobody else can. So when you're talking about competition, it's a little bit hard to compare apples and oranges. But I should say that there is a fabrication process that Greg might remember the name of the company, I'm blanking right now, but they're using ion milling, very expensive, not scalable. So this approach might be able to produce it, but it can't do it economically, would be my comment. But I think these fabrication techniques can probably produce similar size of device for quantum application. Yeah.
So when you say scale, do you mean the number per chip, if you will,
yes.
Or do you mean the throughput of making these?
I mean number per wafer, but that very much translates. So fortunately, the fabrication process is not exceedingly complicated. It's subtle, but it's not exceedingly complicated. So, for example, we can make thousands of such micro mirrors on a 100 on a 2-inch wafer. That scales radically when you start to go to 8 or 12-inch wafers. So this is one of the places we're working is to get this production process working on production tools with foundries, and that will take a little more time and investment. But in the meantime, we have a process that works in an academic fab. So.
And then what modality do you think would be most valuable? Modalities.
Yes. So probably we've seen the most interest from quantum networking, but we've also seen a lot of interest for atomic-based quantum computing as well. So it's a little bit hard for us to predict exactly where that market is going to go and who's going to be the winner, what racehorse is going to win. But I think quantum networking, I'm quite confident that some of these cavities will be very valuable there. Also for quantum sensing. So it's a slightly longer discussion. There's a couple of different regimes of performance where we can really, knock everybody's socks off.
Networking, is that sending it like something from your door to your
I'm not privy to, when we're engaging these customers, we're not asking them to share the whole portfolio on what they're doing, to be honest. So most of the time we're trying to take more of a vendor relationship where we don't ask too many questions and just are your comfortable supplier of integrated photonic parts. But I'm not sure. Actually, that's a good question. Which of these applications